Hello AP Chem students, this is Lou Akampora again from Advanced Kentucky, and I'd like to talk to you right now about advanced atomic structure and photoelectron spectroscopy. This is something that shows up on the AP Chemistry exam. Remember, chemistry is the study of matter, and our goal is to explain how matter behaves in terms of chemical reactions and physical properties, but also why this behavior is expected. This is also a chance for us to not only show what we know, but how we know what we know. So it's a little bit epistemological if you want to get philosophical, as well as ontological. But enough about the philosophy here. So atomic structure, over the last 220 years or so, we've developed a model of an atom, and that model has been refined to fit data. And interpreting data and explaining data is really the hallmark of science. So if you go back a couple of hundred years to Dalton, he had a model of the atom based on experimental results from the law of definite proportions and the law of multiple proportions, where for Dalton's atom, it's really just kind of a blob. And atoms had a characteristic mass, but that was about it. You couldn't weigh atoms directly, but you could figure out what percentage of compounds were composed of each element. So if you knew that water was 89% oxygen by mass and 11% hydrogen, you could work out the relative atomic masses of hydrogen and oxygen. And the same for all the other elements. So for years, the only thing chemists really knew about atoms was their relative masses. And there was a lot of experimentation that went into these values, and some were wrong. And Mendeleev managed to come up with a periodic table in spite of certain inversions in there. But it was the only model that was practicable. In the late 1890s, Thomson, with the cathode ray tube experiment, found that there were in fact subatomic particles. He called them corpuscles. We call them electrons, and that they were present in all matter. And he came up with this plum pudding model, or if you're an American, more of a chocolate chip cookie dough model, where these electrons were negatively charged particles, bits in a jelly or dough that was positively charged, so that the entire atom would be neutral. Now this is wrong, but it does speak to the primacy of electric charge in terms of the understanding the behavior of atoms. Shortly after that, Ernest Rutherford bombarded various metals, notably gold foil, with alpha particles, and found that, well, the atom isn't this homogeneous blob of jelly, but rather has a very small positively charged core that we call the nucleus, and most of the space of the atom is taken up by these electrons. And this is certainly an improvement over the Thomson model, but not quite useful in explaining reactivity. Niels Bohr took a look at the atomic spectra of hydrogen and other elements, and adding a couple of other postulates from classical physics, said, well, this is really we could think about this as having a nucleus, and the electrons are restricted to certain allowed energy levels with various energies, and that the electrons can jump from energy level to energy level, but are forbidden in between there. And this is sometimes called a planetary model. It's the one most of us learn in introductory chemistry or even middle school. And it's very attractive because it looks like a solar system where you've got the nucleus instead of the sun and the electrons circling like planets. It's got some pretty serious problems. First of all, the atoms are not round or flat, they're spherical, and the solar system, you hopefully all know, is rather like a pancake instead of a sphere. Second thing is that the laws of classical physics would predict that these electrons would radiate energy and collapse into the nucleus in a very, very short amount of time, about 10 to the negative 11 seconds for hydrogen. And third, that this neglects the effect of electron-electron repulsion. And yet, this planetary model did explain the spectrum of hydrogen quantitatively, and qualitatively the spectra of all the other elements. Through the late 1920s and into the 1930s, though, quantum mechanics was developed, and we came up with a quantum mechanical model of the atom, our best model to date, because it does explain much of the chemical reactivity. And this quantum mechanical model has the nucleus consisting of protons and neutrons to hold the protons together, but the electrons are really thought of as clouds of negative charge that occupy regions in space or electron densities. And these regions in space have a size and a shape and an orientation, and we call these not orbits, but orbitals. And these orbitals, because of the Pauli exclusion principle, can hold at most 2 electrons, and those electrons have to have opposite spins. It turns out that electrons behave as if they are little balls of charge that are spinning on their axis, either clockwise or counterclockwise. We usually represent those arrows pointing up or down, and that only 2 electrons can occupy one orbital, and if they do, they've got to have opposite spins, or you cannot have 2 electrons of the same spin in the same orbital. So this is our good model of the atom. Photoelectron spectroscopy deals with direct evidence for that. But before we talk about photoelectron spectroscopy, I want to look at something that really was known well before even Dalton, and that is periodicity. If we were to look at our atom with some number of protons, there would be a small orbital, which we call the 1s electron, and because those electrons are closest to the nucleus, they would have the most negative energy. I usually try to show this on an orbital energy diagram, where energy is listed from bottom to top with 0 at the top, since orbitals or bound states have to have negative energy. And our 1s orbital would have some negative energy down here. And that the magnitude of this energy would depend on the nuclear charge. The more positive the nucleus, the greater the force of attraction, and the more negative that orbital would be. So the 1s orbital of hydrogen would be at some level, and then the 1s orbital of helium with 2 protons would be much further down. And eventually you'd get to lithium and beryllium and all the way down to uranium, where you'd be down near the center of the Earth or thereabouts on the scale. The next orbital would also be spherical, and we'd call it the 2s orbital, and it would hold up to 2 electrons, and it would be not quite as low in energy. And then our atom would have 3 orbitals that are of the same shape and size, but differ in their orientation, and I'll call those the 2p orbitals. If I need to, 2px, 2py, and 2pz. And that's it for the second shell. And then we go on with the 3s, 3p, 5 orbitals encompass a 3d subshell, and you can look in your textbook for pictures of those orbitals. And the 4s would be right in there, slightly lower in energy than the 3d. This shouldn't really surprise us, but it does explain the iconic picture of a chemistry class that you've all seen, and that look on the wall of your classroom, and I'm sure you'll see this periodic table, and we know the elements in a particular column have similar chemical properties, and that's because, and those properties repeat itself, because as we fill up a level, as we go across and we fill up the first level with a 1s orbital, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s, and 3d, and 4p, and so forth. The chemical properties of these elements, of the atoms, are governed mainly by the electrons that are furthest from the nucleus. Those frontier electrons are going to be the ones that react, that interact first, and the number of valence electrons, we call them the valence electrons, determines the overall chemical properties, or the major determinant. in the overall chemical properties. Mendeleev worked this out in the 1860s before anyone knew anything about electrons. And later, when this orbital picture was worked out, it was certainly reinforced by the structure of the periodic table. I want to emphasize in terms of vocabulary that when we talk about this and when you write about this on the AP exam, we talk about shells, and shells are really all of the orbitals of a given size or with the same principal quantum number. So the third shell would encompass all of these orbitals. In fact, there are 9 of these orbitals. A subshell would be all of the orbitals with a certain given size and shape. So we talk about the 3s subshell, which comprises only one orbital. The 3p subshell would consist of 3 orbitals, 3p, x, y, and z, if we needed to denote them separately. And then the 3d subshell would correspond to those 5 different orbitals. So orbitals make up subshells, subshells make up shells, and then the entire shell structure is typical of the atom. The numbers of orbitals that are allowed and the number of subshells are allowed come out of quantum mechanics. It's well beyond the scope of AP chemistry, but there's a nice pattern that you should see. And this structure leads not only to reactivity, the number of valence electrons, and the way chemicals bond in terms of losing electrons or gaining electrons. Ionization energy is also an important property that is periodic in nature. And remember, by ionization energy, we mean the energy needed to remove the outermost or most loosely bound electron. So if we had, for example, a nitrogen atom with 7 electrons, we would denote the electron configuration as such, where 1s2, 2s2, 2p3, where for the ground state, Hund's rule tells us that these electrons would all be pointing in the same direction. They would have the same spin and would occupy different orbitals within that subshell. Ionization energy would be the amount of energy required to remove the most weakly bound electron from an isolated gas phase atom. Now, nitrogen atoms would not normally exist under normal conditions. We'd normally have nitrogen molecules that are N2, have the formula N2, but to measure the ionization energy, we'd be talking about nitrogen atoms, which would lose an electron. And the amount of energy required to do this is called the ionization energy, normally expressed in kilojoules per mole. And for neutral gas phase atoms, the ionization energies range from about 500 kilojoules per mole to about 2,500 kilojoules per mole for the first ionization energy. And then subsequent ionization energies would require removing more and more electrons. And we see a trend as we go across the periodic table. The ionization energies tend to increase, with exceptions due to different subshells and orbital filling. But because every time we go across a periodic table, we add another proton to the nucleus without increasing the number of the valence shell. So there's a little bit more of an effective nuclear charge pulling on those electrons. What I really want to talk about today, though, is the direct evidence for this shell structure, and that is photoelectron spectroscopy, something that you're unlikely to do in a high school chemistry lab, but something that is done in research and provides direct evidence for this the now orbital configurations. So photoelectron spectroscopy allows you to measure the energies of these orbitals fairly directly. And let me take a very simplistic picture of a nitrogen atom. 1, 2, 3, 4, 5, 6, 7. And this is a little bit of a shorthand because we know these 5 electrons in the second shell are configured into 2 different subshells. So for nitrogen, we have a 1s2, 2s2, 2p3. That's not really reflected in this model, but we'll just remember that. To probe the energies of these electrons, the binding energies, what we'll do is we will take very, very high energy light, usually X-rays or gamma rays, and light, you likely know, but may not, is a form of electromagnetic radiation. And that's the same whether we're talking about visible light that our eyes respond to, or radio waves, or X-rays, or infrared, or ultraviolet. It's all alternating electric and magnetic fields. And light, surprisingly, is also quantized, exists in little discrete particles. And we call these particles of light photons. And in much the same way that a nitrogen atom is discrete, can either react or not react, but you can't have a nitrogen atom 2/3 of it react or 5/7 of it react. It's either all or nothing. A photon will either be absorbed or not absorbed, and you can't break it down into a smaller particle. So light carries energy in the form of photons. The energy of these photons, there are a couple of formulas. So if we've got this little digression here, if we've got this wave, there are a couple of characteristic values that we talk about. One is the wavelength, the distance between crests or the distance between troughs, and that usually has a symbol lambda. The wavelength measured in meters or millimeters or nanometers per wave. We usually don't say the wave. So we might talk about the wavelength of visible light, green light being 550 nanometers, and the units do matter, so make sure you understand that a nanometer is not the same as a meter. We also talk about the frequency, and some books give it the symbol F, some give it the Greek letter nu, which looks like a kind of curly N. And this would be just how many waves pass you per second. So this wave is moving along, and if this were a water wave and you were sitting here on the pier, you'd count how many waves pass you per second, and that would be the frequency. We usually express that in waves per second. And again, we usually don't say the waves, we just say the frequency in per second or hertz. And you'll tune your radio dial to some number of hertz. And then the wavelength times the frequency gives us a speed, and that should make sense. If I've got, for example, waves whose wavelength is 5 meters and 12 of them pass me per minute, then the wave is moving past me at 5 times 12 or 60 meters per minute. In the case of light, the speed of light is very quick. It's about 3 times 10 to the 8th meters per second. But that's common for every wavelength frequency of light. So the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. The other important formula to know about light is that the energy of a photon, and this is unique to light, this won't work for water waves or sound waves or waves in a guitar string, but the energy of a photon is proportional to the frequency. Oops, I'm going to use nu for frequency here. Where this constant of proportionality, called Planck's constant, has a value of 6.63 times 10 to the negative 34 joules per hertz. So if you have the wavelength or the frequency in hertz, multiplying it by this constant will give you the energy of that photon in joules, and then commonly we'll express energies as not joules per photon, but joules or kilojoules or maybe even megajoules per mole of photons. But to go from the particulate level value of joules per photons to the more macroscopic value of joules per mole, we would just need to multiply by the number of particles in a mole, and that, of course, is Avogadro's number. So we can find the energy of light, of a photon of light. And these are 2 formulas that you'll need to be able to use. You don't need to remember those formulas, they're given to you, and certainly the values of these constants are, but you should be able to use scientific notation because these numbers are ridiculously large or small, and it's very inconvenient to write this out with 33 zeros after the decimal point and then a 663. So make sure you know how your calculator works and how to use it, how to treat numbers in scientific notation. So in photoelectron spectroscopy, you take your sample, your atoms, and you zap them with very, very high energy photons, and the photon will hit an electron and kick it out. And that's the photoelectron, the electron that is kicked out. And this electron will be kicked out with some kinetic energy which can be measured. Your photoelectron spectrometer will actually be able to measure the kinetic energies of these electrons. And since energy is conserved, the energy of the photon is equal to what we'll call the binding energy of the electron plus the kinetic energy of the electron, the energy of motion. And since this can be measured and this can be measured, we can directly calculate that. Or if you would prefer, we can write the binding energy, which is really the energy of the electron in the orbital, although this is normally a positive value. And remember we said the orbital energies are normally negative, so it's the positive value needs to remove it. But it's going to be equal to the energy of the photon plus, minus the kinetic energy of the electron. So that is really the only equation for photoelectron spectroscopy. The important thing for photoelectron spectroscopy as opposed to ionization energies or visible light spectroscopy is that these photons have enough energy that they can remove even those lowest energy innermost electrons, which means that they're going to have energies in the range of megajoules per mole. So you got to use really, really short wavelength, high energy photons to do this. And then you'll see that your typical output for a photoelectron spectrum will show peaks corresponding to the binding energies of these electrons. So your photoelectron spectrum. In the notes that accompany this video, you'll see a printout of an actual photoelectron spectrum. Anything you're likely to see on the AP chemistry exam will be very, very sanitized and cleaned up a little bit. But typically there'll be a scale here of binding energy. Because these energies range from fairly small, some number of kilojoules per mole, to hundreds of megajoules per mole, this is often a logarithmic scale. So pay a little bit of attention to the scale. Let's say this is in megajoules per mole, and there might be 0.1 here, 1 here, 10 here, and 100 here, and even more if we need it. And then on the vertical axis, we'll see the relative intensity, which is related to the number of electrons in that energy level in the sample. So if we had a sample of nitrogen, we would expect to see 3 peaks. We'd see a peak corresponding to those 1s2 electrons, and that would have the greatest binding energy. So it would be off to the left here because binding energies increase going right to left. And without worrying about what the value would be, we might see a peak here of intensity level 2. We'd also see a 2s peak of the same height, but out here somewhere of roughly the same height. Oops, let me fix that a little bit. And then we see pretty close to the 2s level, a 2p peak, and that would be 1.5 times this height. So we would expect this to be the complete photoelectron spectrum of nitrogen. And you might see actual numbers here that tell you what the binding energies of those electrons are. So that's really it, and there's not too much more to interpret. There are a couple of sample questions on your handout, so I'd encourage you, if you're watching this on video, to pause the video here and maybe try to answer those questions yourself, and then I'm going to go over them in just a minute. So this would be a good time to hit the pause button. Okay, we're back. Sorry. So sample question 1, actually we just answered that. You're given a PES spectrum and it looks a little bit like this, and asked what element could be represented by this complete spectrum. And again, you're always going to go left to right, and this will be the lowest energy level, the 1s level, and except for hydrogen, it will have 2 electrons in it. So 2 plus 2 plus 3 would represent a total of 7 electrons, and that would be nitrogen. If you look at sample question 2, it shows you 2 spectra, one for lithium and one for beryllium. And I'm going to go ahead and very quickly reproduce these on the board here while you take a look at that. So without putting in the axes or the numbers, for lithium, we have a peak that is, at 0.1, there's 0.1. So lithium has a peak that's right about here. And this one is not in a logarithmic scale, so because we're only really looking at one peak. Beryllium, our beryllium atom, so has 4 protons in the nucleus. Remember, the most important thing about an atom is the number of protons in the nucleus of the atom, and this is just the way chemists count, where most people would count 1, 2, 3, 4, 5, 6. Chemists count hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and so forth. So for beryllium, we've got a peak that's over here. And 2 things to notice about this peak. And you're told that these peaks correspond to the 2s orbitals. You're asked to explain the relative positioning. Well, and intensity. The intensity is pretty straightforward. The 2s subshell in lithium only has 1 electron. The 2s subshell in beryllium would have 2 electrons, so that peak would be twice as high. The relative positioning has to do with the nuclear charge and the fact that these electrons are attracted more strongly to a nucleus with 4 protons than a nucleus with 3 protons, and therefore would have a greater binding energy. So if you look at sample question number 2, I think A would be the best answer for that. Question number 3, sample question 3, is a little bit more involved, and it involves spectra for phosphorus and sulfur. So I'm going to go ahead and try to reproduce these very quickly. For phosphorus, we see, without the numbers, we see a 1s peak, we see a 2s peak, we see a 2p peak, that is 3 times as high, we see a 3s peak, and then we see a 3p peak. And then for sulfur, we see very similar peaks that are slightly displaced to the left, except for this last peak, which is taller and shifted to the right. So this is phosphorus, and there's my sulfur atom. And remember, the phosphorus atom has 15 protons in the nucleus. The sulfur atom has 16 protons in the nucleus. So if we look at these and say, why is this happening? Well, for the most part, most of these peaks in sulfur are shifted to the left, and that's because we've got an extra nuclear charge here. But what about this last peak on the right, which is the 1s, 2s, 2p, 3s, 3p peak? For phosphorus, the 3p subshell has 3 electrons. In in sulfur, that 3p subshell would have 4 electrons, and that 4th electron means that one of these orbitals is going to have to double up. We're going to have to put 2 electrons in the same orbital. These 2 electrons are not attracted to each other. They still repel each other, but because they are attracted to this nucleus with 16 protons, they will tolerate each other. Well, as you might guess, putting 2 electrons in the same orbital means they're going to be closer together than otherwise, and it means there's going to be a repulsive force between them that will make it slightly easier to remove those electrons. So this additional electron-electron repulsion that occurs when you have 2 electrons in the same orbital that is present in sulfur but not in phosphorus will account for this anomaly. So I think the best answer here is, again, A, where sulfur has a greater effective nuclear charge than P, but the 3p sublevel has greater electron repulsions than P. Question 4, and we'll go through these pretty quickly, I think. There's a 4a and a 4b, and these deal with the photoelectron spectra of sodium and potassium. Let me just start again here. And notice again, this is not a logarithmic scale, and that means all these peaks are crunched up to the right, and they're not the same scale either. So we've got sodium here with 0 and 130 roughly here, and we've got a peak close to 105, and then peaks over here. And then for potassium, also a linear scale, but this time we go all the way down to 400. So we have a peak that might look like it's in the same place, but that's deceptive because this 1s peak is really at 350 megajoules per mole, not the 105 megajoules per mole. Put that down here. And then we see 2s, 2p, (3s) and 3p. And the 3s peaks are going to be here and here. So in sample question 4a, they kind of expand that for you, and they ask for the best explanation for the difference in binding energy between the 3s electrons. And since sodium has 11 protons in the nucleus, potassium has 19 protons in the nucleus, the greater nuclear charge would account for the difference in binding energies. Question 4b asks you to explain the difference in signal intensity for those electrons, noting that the potassium signal is twice as great as the sodium signal. And again, sodium, that has to do with the number of electrons. Sodium has got a neon core, 3s1. Potassium has that neon core, 3s2, 3p6, 4s1, which we would normally write as an argon core, 4s1, but I've kind of split that out so you can explicitly see the 2 electrons from the 3s subshell. Last multiple choice question, but question 5 asks you why scandium would commonly form ions with a +3 charge, and it looks like those on the right-hand side here for scandium. These lowest binding energy electrons, the ones that are most easily removed, there are 2 peaks corresponding to 1 electron and 2 electrons respectively. This would be our 4s electron, 4s2, and our 3d1. And because those are both have very low binding energies, they can be removed. So I think the best answer to that would be letter C. The amount of energy required to remove electrons from the 3d sublevel is close to that for the 4s sublevel, but significantly more energy is needed to remove electrons from the 3p sublevel. It would be down around there. Some draw your own spectra. So let's take a look at these last questions, a few more questions here. If we're given the spectrum for magnesium, and by now I think many of you can predict this yourself. Intensity here, megajoules per mole, and we'll have 0.1, 1, 10, 100. So magnesium, it looks like the magnesium's got a peak here, which would be the 1s peak, or a little bit more than 100. A 2s peak, a 2p peak, and a 3s peak. And now on that same scale, we're asked to sketch a spectrum for aluminum. Now remember, magnesium would have a nuclear charge of 12. Aluminum would have a nuclear charge of 13. So we'd expect these peaks to be shifted leftward toward higher binding energies. So there would be my aluminum 1s peak, my aluminum 2s peak, my aluminum 2p peak, the 3s peak. But now aluminum would also have one peak at the 3p shell, so we'd have another peak here. And the relative positioning is rather arbitrary. I'm not sure exactly where they would be, but they'd want to be to the left of those peaks for magnesium, since there's nothing really funny going on. It's kind of unusual to have photoelectron spectra for noble gases, but it is possible. You've got to cool them down to condense them. But if we had the peak for neon, and let's go ahead and set that up, 0.1, 1, 10, 100. So our peak for neon would, we have a, let's see, this will be neon, we've got a peak right here. That's my 1s peak again. Peak for 2s electrons right here, and then a peak for the 2p electrons, 1s2, 2s2, 2p6. What would you expect to see if we had solid the ionic compound sodium fluoride? Well, let's think about sodium fluoride. Sodium fluoride is composed of ions of sodium and fluorine. And each of these ions are isoelectronic to neon atoms. They each have 10 electrons, but sodium ions would have 11 protons. Fluoride ions would have 9 protons. So we would see two sets of peaks. We would see the peaks correspond to the sodium, which would be to the left to higher binding energies. So this would be the sodium 1s, 2s, and 2p. And then I'll do these in green, but we'll also see peaks for the fluoride ion, the 1s, the 2s, and the 2p. I'll get rid of our neon spectrum, and there would be our sodium fluoride spectrum. So you see, you can actually have peaks from two different ions in the same spectrum. It gets a little bit more challenging, but not much more, if we had not sodium fluoride, but magnesium fluoride. So MgF2, we would have magnesium ions with a charge of +2 and 2 fluoride ions. So the magnesium peaks would actually be even more to the left, and because there are half as many of them, they would be half as tall, or half as intense. So I might represent that like this. So this would be the magnesium 1s, the magnesium 2s, and the magnesium 2p peaks. So I hope that's not too much. That's probably the most complicated one I've seen, and unlikely that, but you'll see anything more complicated than that, but I think it's understandable. I want to do one more quantitative question using those formulas that we looked at, and that's that last question, question 4. You're given a complete photoelectron spectrum of a pure unknown element, although by now you could all figure out what the element is by counting electrons. So we've got a peak down here at 221 megajoules per mole, and that's the 1s peak. We've got another peak here of the same height, and that's our 2s peak, our 2p peak, our another peak here, and then our another peak here. That looks like that. And the first question is, if you've got this atom and you're going to zap it with a photon, what's the minimum frequency needed to ionize this, to create that peak? And that means the energy of the photon has got to be greater than or equal to 221 megajoules per mole. So how are we going to turn that number into a frequency? And there are 2 steps. The first thing we've got to do is convert that to joules per photon. Since we don't want a mole of photons, we just want a photon. And to do that, we'll divide that number by 6.02 times 10 to the 23rd, the number of particles in a mole. And remember that 221 megajoules would be 221 times 10 to the 6th joules per mole, divided by 6.02 times 10 to the 23rd. I'll call that photons per mole. And now my per moles cancel, and I've got joules per photon. And let me go ahead and do that arithmetic over here. And again, make sure you know how to use your calculator and to use scientific notation. So that's 221 times 10 to the 6th divided by 6.02 times 10 to the 23rd. And I get 3.67 times 10 to the negative 16th. And you expect a pretty small number of joules, because in one photon is a pretty small bit of light, even though that's a huge amount of energy for just one photon. Since the energy is equal to Planck's constant times the frequency will be the energy over Planck's constant, that's h, and I'm going to take my 3.67 times 10 to the negative 16th joules per photon, and divide it by 6.63 times 10 to the negative 34 joules per hertz. And I'm going to be left with hertz. We don't usually write the per photon. So I'm going to take that number that's conveniently there and divide by 6.63 times 10 to the negative 34 and get 5.53 times 10 to the 17th hertz. So that would be firmly in the X-ray region, very damaging photo radiation. But you know, the skills here are to go from a macroscopic value of megajoules or kilojoules per mole to a particulate level number by dividing by Avogadro's number, and then using this formula and doing the arithmetic correctly. Part B here asks you from what energy sublevel are electrons removed that generate the peak marked X, and we've already answered that question. That peak corresponds to the 3s sublevel. Remember, the sublevel is both the number and the letter, and a little trivia for you. Those orbitals are S, P, D, F designations, and those don't stand for spherical or anything. Many students think the S stands for spherical. They actually stand for sharp, principal, diffuse, and fundamental, which was the spectroscopist notation for the lines in the spectra of these elements back in the 1800s, before we knew anything really about electrons. And then the final part of this question asks you where we would be removing electrons for the second ionization energy. And this, by the way, is a phosphorus atom. So the first ionization energy corresponds to this process. That's IE1. The second ionization energy would be just what it sounds like, removing the second electron to generate a positive 2 ion plus an electron. Well, since we've got 3 electrons in the 3p subshell, the first 3 ionizations would all remove electrons from that 3p subshell. So the second ionization would be removing electrons from that 3p subshell. Well, that's all I've got. I hope that might be helpful. Again, feel free to let me know if you have any questions. Ask Lou, KY, or elacampora@kscc.com. And good luck with your AP Chem